Mercury is a very interesting element. It's one of the toxic elements. It occurs naturally, and we have anthropogenic sources of it also. We're mostly concerned with methyl mercury. That's what you hear about most often because that bioaccumulates in biological systems. There are natural sources of mercury, including volcanoes, forest fires, and the volatilization of mercury ore. And the volatilization of these things usually cause elemental mercury to be released into the atmosphere. And that atmospheric mercury then can precipitate down into the aquatic systems, and then it can again volatilize from the aquatic system back into the atmosphere. There are also anthropogenic sources. The combustion of fuels. We talk about medical waste, incineration, and also coal-fired power plants. And again, we can get elemental mercury, a mercury attached to some particulate matter in the atmosphere, precipitates into the aquatic systems, and it can volatilize again. So aquatic systems are very important for mercury sources. The inorganic mercury is now considered the predominant source of mercury for methylization. And recent studies have indicated that approximately 30% of mercury emissions come from coal-fired power plants. And so, and the mercury that's available, inorganic mercury, can be both inorganic and organic mercury are toxic. The inorganic mercury can become methylated. In this particular slide, the reason that methyl mercury is so important, the yellow numbers are total mercury concentrations, and the red numbers are those that are considered to be methylated. And you can see in lower organisms and aquatic systems, we have low methyl mercury, but as we move up the food chain, when we get up to some of the larger vertebrate species, almost 100% of the mercury in those species can be in the methylated form. So methylated becomes very important mercury source for our top predators. We're concerned with wetlands because wetlands are the source of the methylation that's occurring in a lot of systems. The freshwater systems can be both a sink and a source. As we get atmospheric precipitation or runoff, we get mercury accumulating in the aquatic systems. And then, especially in aquatic systems that will dry down periodically and reflood, and during flooding periods, then we have the mercury that can move from these wetland systems into rivers and lakes and become a source of methylated mercury to other systems. Now there's a concern with the different types of mercury. Typically the particulate mercury will precipitate out of the atmosphere pretty quickly, so we consider that to be a local source of mercury. And then there's kind of a regional source of the inorganic mercury, and then the elemental mercury is usually on a global scale. And actually mercury is one of the few metals that has, every 2 years there's an international conference on mercury as a global pollutant. So it's a lot of concern, environmental concern worldwide. Because of these particular issues, we did a study looking at mercury concentrations in wetlands associated with coal-fired power plants. Dr. Scott Weir is my student. He's now working on his PhD at Texas Tech, and he's the one who's involved in this study. And we received a seed grant from the Sustainable Research Center for this particular study. our objectives is a preliminary study to get some preliminary information about total mercury concentrations in wetlands that were associated with coal power generating plants. We had two major hypotheses. The first hypothesis was that sediment and tadpole total mercury concentrations would be higher downwind relative to upwind of coal power plants, and that the concentrations would increase as we went downwind of the coal power plants. The second was that sediment and tadpole total mercury concentrations would be positively correlated. We also wanted to develop, because it was a preliminary study, some specific protocols for monitoring mercury concentrations in wetland habitats. So we went through a process of selecting power plants, and our selection process involved what was the mercury emissions from the particular power plants, were there prevailing wind information, data for those particular power plants, were there suitable habitats associated with them, and the plants that we selected were the Joppa, Baldwin, Newton, and the Southern Illinois Power Cooperative power plants. The samples were collected in May and June of 2007. We got 45, had total 45 total wetlands that we collected samples from. 12 wetlands were associated with Baldwin and the SIPC. We had 11 wetlands for Joppa and 10 from the Newton power plant. So the method was to select wetlands upwind, and we wanted 3 wetlands upwind that were between 3 and 5 kilometers from the plant, and we wanted 9 downwind locations, 3 each at 3 to 5 kilometers, 8 to 10 kilometers, and 3 to 15 kilometers downwind from a particular power plant. This is a map of one of the particular power plants, and the star indicates where the power plant is, the prevailing wind direction, and the little triangles are where the wetlands are. So you can see in this particular situation that one of the problems you have is where are your wetlands. This one is pretty good location downwind from upwind. In this particular case, some of the wetlands were not really available straight downwind from the particular power plant that we were interested in. And again, look at this particular power plant. The power plant location are 3 located upwind, and then the location of downwind plants. So logistically, trying to find 3 wetlands that were 3 to 5 kilometers downwind, and 3 wetlands that were 5 to 10 kilometers downwind, and 13 to 15 kilometers downwind was sometimes a little bit difficult to do. Sediment samples were collected we're using a core auger, so we went to the different wetlands and we collected 3 core auger samples from each of the wetlands. We also measured temperature, overlying temperature at the site where the sediment was collected. We collected tadpoles opportunistically using dip nets, and those particular tadpoles then were identified as species, stage of development, and mass and length were recorded. Sediment samples were brought back. We also determined the redox potential, pH, and texture for the individual sediment samples. And we measured mercury. We measured total mercury concentrations in tadpoles using a AF cold vapor mercury analyzer in our laboratory. And the tadpoles were digested following EPA method 245.7. Sediment samples were digested and analyzed here at the ISTC. We evaluated the data using SAS version 9.1, looked at normality of the data. We did analysis of covariance, analysis of variance, and then correlations using Pearson correlation. This is the sediment data, and the different power plants are listed over here. And The red line is for the Newton power plant, and actually the Newton power plant was the only power plant where we saw a significant increase in mercury concentration downwind of the power plant. These locations at 1 are the ones above the power plant, and this is 3 to 5 kilometers downrange, 8 to 10 kilometers downrange, and 13 to 15 kilometers downrange. So we've got quite a variety of variation in some of the concentrations. And you'll notice over here we're looking at the log of the sediment concentrations. So the Newton power plant was the only one where we saw a downwind change in mercury concentrations. And if you look at that on the bar graph again, the Newton plant was the only one that had a significant difference. These are tadpoles. And again, when you're doing this type of study, you go to you've identified a pond, and you go to the pond, doesn't mean you're going to find tadpoles there. We found tadpoles at 29 of the ponds, and we were looking primarily for bullfrog or green frog tadpoles. And these are the mercury concentrations we measured. The majority of our samples were homogenized for analysis, but we were wondering if we had the homogenation process was affecting the mercury concentrations that we were measuring. So we actually measured some tadpoles whole, and the only concentration was in green frogs that were measured whole. But when we adjusted this for size, then there was no significant difference between whether it was a bullfrog or a green frog tadpole, or whether it was a homogenized sample or a whole sample. Looking for the different power plants, again, we had no significant difference in the mercury concentrations in our tadpoles comparing any of the distances. So comparing 3 to 5 kilometers above the power plant or below the power plant, we had no significant differences. But we did have some trends. Here's the Newton power plant again, and that was a power plant where we had a significant difference in sediment concentration, and we had a trend towards a greater concentration in tadpole concentrations downwind relative to what we had above the power plants. Again, here's the data in a bar graph. Again, no significant difference, although, again, it was the biggest trend appeared to be here in the Newton plant. So we wanted also to look at concentrations that were important. When we say important concentrations of concern. So here is some published information on concentrations that were concerned. This is for sediment, total mercury concentration. These are all in dry weight concentrations. And background concentrations reported in the literature, and here's some references for this particular data. Here's our data, and here's concentration of concern in sediment. For aquatic vertebrates, again, background concentrations, what we measured in our study, and then concentration of concern. So we see that our concentrations are all, and again, these are ranges, so these are the highest concentrations that we measured in our sediments or our tadpoles, were all below concentrations associated with concern. We did find some interesting information, though, in our study. These are looking at mercury concentration and Gaussian stage of the particular tadpoles, the total length of the tadpoles, and weights. One of the interesting things that we found is that mercury concentration was negatively correlated with the Gaussian stage, total length, and weight, which is kind of counterintuitive to what we were thinking. We would think that as the tadpole got bigger, then the mercury concentrations would also increase. And it may have something to do with the changing of the feeding habits of the tadpoles over time. But it was interesting that the highest mercury concentrations then occurred in our smaller tadpoles rather than the larger tadpoles we were looking at. But we did have the Gaussian stage and total length were correlated, and the weight and total length were correlated, which you would expect to find. Now, if we look at some other studies that have looked at tadpoles, these are field studies, not laboratory studies. This is our current study and the information we found with green frogs and bullfrogs, looking at the whole body. And here's the mercury concentrations that we measured. Other studies in Savannah River were done in 2001 using southern leopard frogs, and they used body, tail, and digestive tracts, and all of their concentrations were below 0.2 nanograms per gram, which is their detection limits. Studies done in Arcadia National Park using bullfrog and green frog, and this was probably the one that's most closely related to the studies that we've done, and they found concentrations were a little bit lower than the concentrations that we measured in our tadpoles. These concentrations here are given in dry weight by this particular study in Savannah, again, Savannah River, using southern leopard frogs, using carcass and gut content. So in that particular case, they took the carcass, removed the gut content, and measured it. And these were their concentrations. For comparative purposes, we did have some tadpoles where we were able to measure percent moisture and able to calculate dry weight. And so our mean dry weight concentration was about 312 nanograms per gram for the tadpole carcasses. Highest concentrations here on a wet weight basis for these were from Yugoslavia, and they didn't provide very much information in this particular paper, but they were much higher than the concentrations that we measured in our particular tadpoles. Other studies that have looked at coal-fired power plants. Again, on the bottom here, we have our particular study. Another study in 1977 in Illinois. This is looking at concentrations in one lake and also looking at terrestrial soils less than 15 kilometers from a coal-fired power plant. They looked at some fish species, and this was a new coal-fired power plant that was coming into existence, and their soil was significantly greater downwind than upwind, and the lake sediments were greater after the beginning of the operation of the particular plant, and fish concentrations were very low. So that one showed some significant differences downwind versus upwind. The rest of these we're looking at, all the concentrations that either did not fluctuate with distance or 9 elements that they looked at. In this particular study, they looked at concentric rings around the power plant and found no pattern. And also in this the last one here, there was no pattern in concentric rings. And they actually had modeled ahead of time what they anticipated finding, but the model did not match what they actually found in the field. And again, in our particular study, there was no pattern for 3 of the coal-fired power plants. We did find that with the new power plant, sediment concentrations were significantly increased downwind, and we had what we would call a trend right now for increased concentrations in tadpoles, although it was not significant. So are tadpoles good as bioindicators? In this particular graph, we're plotting the sediment concentrations with the tadpole concentrations, and you see that there doesn't appear to be much of a correlation between concentrations that we measured in our tadpoles and concentrations that were in the sediment for the ponds that we evaluated. So if we go back and look at what our particular objectives were, again, a preliminary study, we wanted to look at mercury wetlands associated with these coal-fired power plants. For our first objective, we wanted to determine if sediment and tadpole mercury concentration, we predicted that sediment and tadpole mercury concentration would be higher downwind, and that concentration would increase as we went further downwind. And this was only true for the new power plant in sediment. That was the only one that found a significant difference, upwind versus downwind. And for our second hypothesis, that sediment and tadpole total mercury concentration would be positively correlated, and we would have to reject that because we didn't find a positive correlation between concentrations we were measuring in sediment and concentrations we were measuring on tadpoles. And but we developed this protocol for using this particular technique in wetlands. Management implications from a management standpoint. The mercury that we measured in the sediment and tadpoles surrounding the Newton, Joppa, Baldwin, and CIPS coal-fired power plants were all below levels of concern. So that's a good thing. At least nothing that we measured was a particular concern from a management implication standpoint. I'd like to thank the Illinois Sustainable Technology Center for the seed grant that we used, Gary Bortson and the Metals Group here for doing the analysis on our metal samples. Mark Awani, I'm glad he's here today. He was the one who initially helped with us when we got the seed grant. The Cooperative Wildlife Research Laboratory at Southern Illinois University in Department of Zoology and Graduate School at Southern Illinois University. If there's any questions about that, yeah.
Why did you expect Mercury
we thought that in the power plants, the mercury goes up in the fumes and stuff, and then we would expect precipitation. And we just thought that probably the concentrations, the amount of deposition would increase as you went down wind. That 3 to 5 kilometers wouldn't be far enough to get a lot of deposition from the power plant, given the height of the power plants and the movement of the atmosphere.
We weren't expecting any dispersion.
We're expecting some
Dispersion, which spreads things out.
Yeah, we were expecting that. I mean, we could have, other studies have looked at concentric circles around plants, and that's another way of looking at it. And our methods and protocol that we developed, we decided to try to look and see if there was a downwind versus upwind concentration. So there is some dispersion that would occur, but we would still expect that the downwind movement would be the prominent movement of the mercury from the plant. Yes.
Do you notice any malformation of the tadpole?
We didn't find any malformations of the tadpoles.
What exactly is a tadpole?
The tadpole is the long. That's a tadpole. It's the larval stage of the frog before it metamorphs into an adult frog.
And bullfrog?
Pardon, that's bullfrog.